Welcome to day 3 of the virtual main event. We're excited for another day of news and analysis from a terrific lineup of experts. Yesterday we spoke with RSM, the global consulting firm, about ways technology and blockchain networks support commerce and how they are likely to affect risk and insurance management. We also learned about the value of community engagement in risk awareness, risk management, and risk mitigation from an international fire protection expert from the UK. And we had COVID-19 reports featuring NAMIC CEO Chuck Chamness. Today, we'll look at the way technology is affecting data management and information sharing in the insurance industry. We'll explore the strength insurers are finding in numbers coming from the modern home with leaders from NEOS, CFM, and Roost. We'll turn our spotlight on insurtechs in the builder's risk market with Vendati. All before we welcome Greenberg Trowrig's own Fred Karlinski to join us for a very special COVID-19 report. Remember, throughout today's broadcast, you can ask questions of moderators and guests by posting them using the app below. If we do not get to your question live, we will post answers online afterwards. As a reminder, please visit the virtual marketplace during breaks in the action. You can learn more about the great sponsors that have helped make the VME possible. Kicking us off today is our own Joan Zerkovich, head of AAIS operations, with a spotlight on modernization. Joan will share lessons learned from the birth of the internet from personal experience. Then Joan will have the distinct pleasure of talking about these developments with the father of the internet, Mr. Vint Cerf.
Well, thank you, Ed. And as you know, we have talked quite a bit at AAIS and in OpenIDL about the parallels that we see in how the internet developed and how we see blockchains developing. And hopefully we've selected the best practices in the development of the internet and applied that to the OpenIDL. So I'd like to talk a little bit about where the internet started. I had the fortunate experience of being hired by the University of California at Davis as the first network administrator for the campus, just at the time when the National Science Foundation was beginning their initiative to connect the supercomputer centers all across the country to the researchers and the professors and the universities that needed access to these platforms. So at that time, the National Science Foundation was looking for a networking technology that they could use to meet the needs of this very large community. Now, there were commercially available proprietary networking technologies at the time. They were available from IBM and Digital Equipment Corporation, Hewlett-Packard, and there were also some other proprietary networks that had been built by the computer science communities, the high-energy physics communities. But these were proprietary networks that had been built for small communities as well. But the National Science Foundation, when they looked at TCP/IP, which was an open standards-based network that had been developed within the Stanford research community working with the ARPANET, it had real practical experience behind it. TCP/IP, it had all the characteristics that they needed for this national network that would develop over time beyond the immediate need of connecting these supercomputers together. So they selected TCP/IP as the networking standard for this network. And the research community began building an open platform, an open network using this technology. The network was built with two key aspects to it that made it successful. So first, there was an operating system available from the University of California at Berkeley, a version of the Unix operating system that enabled the software developers to create new applications, new solutions inside this Unix operating system. And then they were able to share that with the broader community. And that enabled the rapid development of the network based on real practical experience. And at the same time, the National Science Foundation was encouraging the universities to invite commercial entities to connect to this network. They saw this as critical to establishing the sustainability of the networks financially and to develop the network, having these other technology partners come in and develop the technology as well. So with this open standards, freely available software and partnerships with new commercial entrants into the network grew very quickly and met the needs of the NSFNet and beyond that. And so eventually the NSFNet transitioned into being the commercially available internet that we know today. But through that success, again, with the Unix operating system once being open, an open standard, an open platform, commercially available software, commercially available Unix became available. It was available again from the same technology providers. We had IBM and HP and Sun Microsystems. And they added a lot of value to the Unix operating system, but they also added complexity and cost. And so that accessible, low-cost platform for developing applications on the network, that was being deterred a little bit by all of the proprietary solutions that were being deployed. So in 1991, there was a computer science student who wanted to make a version of Linux that was open, again, an open standard. It was readily available so that the computer science community, the software developers, could go back to that rapid development of new networking technologies. And that's where the operating system Linux was born. So Linux has been extremely successful, and it's now running on more than 90% of the servers that run on the internet today. And in order to make sure that Linux is always available to us as an open source operating system, a not-for-profit organization formed, the Linux Foundation, and they are the stewards of the Linux operating system going forward. And they have positioned themselves to help steward other open source technologies as they continue to develop for the internet. So as we look at the parallels now between the internet and the blockchain networks that are developing today, we see the same thing happening again. We see small communities coming together and developing blockchain networks, data networks, they're a network, on top of these proprietary solutions. And they are meeting the needs of the communities that they're serving today. But they are not positioned to scale to the large-scale national and international needs that might be needed in the future. So when we look at what is available to us that is similar to the internet, we move to the open source community and we see that there is an open source blockchain technology, Hyperledger Fabric, that is available from the Linux Foundation today. And that is the platform that is being used very often to create these broader networking solutions that organizations such as the OpenIDL are developing. So we looked at how did the internet develop, how are blockchain networks developing, and in the development of the OpenIDL, we first went back to that it needed to be based on open standards. We know that the success of any broad-scale network has to have that open platform that meets the needs of a broad community and provides a platform for development on top of that. We also look to open source software. Since the emergence of Linux, many other software solutions that are used to run the internet today are adopted by an open source community and continue to be developed in these open source consortia. So the software that we selected for the OpenIDL platform uses the same open source software. And if you look inside your organizations today, you'll see that your technology strategy, the services that you're using today, whether you knew it or not, all of these open standard, open source technologies are actually integrated into what you use in your business today. And so we've done the same thing with the OpenIDL. We've built our platform to be completely consistent with those technologies that are being used today within our members' IT departments and with a broader community that we hope will be using the OpenIDL in the future. The last piece to think about in terms of the success of blockchain networks is in the financial model that makes a inter-network successful. Instead of a proprietary closed network, what's really important is that the network provides an infrastructure. The OpenIDL is initially built to serve the insurance community for regulatory reporting. That's something that AAIS understands really well. We've been working in in regulatory reporting for 80 years. And so we have built the OpenIDL network to support that specific application. And through practical experience of actually using this technology to build solutions and to build the network, we've been able to incrementally improve the OpenIDL over time. But just like with the NSFNet, we can't really see all of the ways that this technology might be used in the future. We need to provide a network, and we'll fund the network, and the network will meet the needs of our initial group, the insurance community, the regulators, the carriers. AAIS is an advisory organization, but we will establish that platform in parallel to the way the internet and other open source consortia operate, so that when new members enter the network and they have new applications and services that they would like to deliver across that network, we have a platform that they can build upon and not be constrained by some financial model that we built into the network. The network itself exists to support not-for-profit and for-profit applications that would be developed in the future. So that's our perspective on how the internet, blockchain networks, and how the OpenIDL have parallels, and we think the best way to move forward into the future. We're here today to talk about emerging data networks and some of the challenges developers are facing in building these networks, to talk about the key principles that made the internet so successful in its development and how we might apply those principles to new data networks to ensure their success. Joining us today is Vint Cerf. He is the Vice President and Chief Internet Evangelist for Google. And in that role, he is responsible for identifying new technologies that can be incorporated into internet-based products and services for Google. And I can't think of anyone more qualified for that role. Vint is the co-author of TCP/IP and Architect of the Internet. He is the recipient of the U.S. National Medal of Technology and the ACM Alan M. Turing Award, which is often referred to as the Nobel Prize of Computer Science. Vint, thanks so much for joining us today.
It's a real pleasure to be with you, Joan, and to have a chance to talk about the current and future internet and the many other things that are sitting on top of it now that we're using more and more as the pandemic continues. And of course, we are doing exactly that in this conversation.
Mm-hmm. In the early development of TCP/IP, you were primarily working with the military and research communities. And at that time, the National Science Foundation was looking to build a national network. They wanted to connect supercomputers together. The idea was to build regional networks and to connect them all together. And they had a lot of different technologies they could have selected at the time to build the network. There were commercially available network technologies from IBM, Digital Equipment Corporation, HP. There were international standards under development. There were proprietary networks being developed by the research community. But the NSFNet selected TCP/IP. What were the key features of TCP/IP that made it the clear choice to build NSFNet?
It's funny, the way you asked the question, it reminds me of the "what were you thinking" kind of question. The person that made that decision, by the way, was Dennis Jennings, who was on loan to NSF to run the supercomputer program from Trinity University in Ireland. And he made the decision, at least as I remember it, based on utility. There were many other choices, but many of them, as you point out, were proprietary, which limited which kinds of computers could be interconnected. And the original purpose behind the internet design was, in fact, to allow multiple kinds of packet switch networks to be interconnected. And so the ones that we were using as the prototypes were a mobile packet radio system, a packet satellite system, and the original ARPANET, the predecessor to the internet, which is based on dedicated telephone circuits connecting the packet switches together. So we had a pretty diverse collection of networks to be interconnected, and had a very diverse collection of computers to be interconnected. And the beauty of the internet design is several-fold. The first one is that the basic internet protocol has no clue about what is transporting the packets. This ignorance is deliberate. We wanted to be able to sweep new communication technologies into the internet architecture which is layered, just as the original ARPANET design was. So when optical fiber came along, for example, it was not hard to simply sweep that into the system because optical fiber carries packets just as well as radios do or dedicated telephone lines. So that ignorance and openness to new technology was very important below the level of IP. Above the level of IP, there's a similar kind of ignorance and openness. The packets have no idea what they're carrying. All they know is they have a bag of bits. They have to be delivered from point A to point B. The interpretation of the bits is a function of the higher layer protocols and applications, which means if you have a new application, you just reinterpret the bits at the edges of the net. The network itself has no idea what the applications are and doesn't care. Now, it's fair to say that the parametric shape of the network will determine what applications can work and which ones cannot. So in the early stages of internet design, we had a fairly low data rate in the backbone. It was 50 kilobits per second on the ARPANET, for example. You couldn't do a whole lot of video with that. But as time has gone on, of course, the bandwidths of the network have gone way, way up. Now we're talking about hundreds of gigabits per second. And lots and lots of capacity has allowed new applications like the one that we're using at this moment to be implemented on a very large scale. So the technical openness of the system was very important. The other openness in the system was that we published everything openly. No one had to pay for access to the protocol designs. We had an extremely wide open community of protocol developers and implementers. What is now called the Internet Engineering Task Force doesn't even have a membership list. You can't actually join. All you can do is show up. And so this openness, I believe, in many different dimensions, has allowed the internet to serve well. And it certainly convinced Dennis Jennings that it was the right horse to ride, even though there were competitors. We won't go through the list of other public ones, but X25 and the Open Systems Interconnection Model are two other examples. Pragmatics, practicality, availability, and the fact that it was cheap, I think, was the determining factor.
Yep. And certainly the early networks, they were primarily for the research and education community, but at some point the National Science Foundation opened it up and asked the regional networks to bring in commercial entities into the network. And I'm sure they came with their own ideas of how the network should be developed, the type of applications that should be developed on top of the new networking protocols. How important was that cross-industry pollination, the collaboration between the groups to the development of the internet? And do you have any thoughts about what would have happened if it had been restricted just to education and research?
Well, it actually was restricted to education and research all the way up till about 1989. And so it's actually important to understand a little bit of that history. The internet was capable of handling multiple networks, which led NSF to design the NSFNet backbone and to underwrite the cost of intermediate level networks, although they said that their underwriting would eventually dissipate and they all had to find business models that were self-sustaining. But up until 1989, it was not permitted for any commercial traffic to be carried on any of the government-sponsored backbones. So that included ARPANET, NSFNet, the ESNet from the Department of Energy, and the NASA Science Internet. But around 1989, I made a request of NSF, or actually of the Federal Networking Council, which was responsible for policy in the US Internet, to connect the MCI mail commercial email system to the internet. In this case, it would have been to the NSFNet backbone. And there was a discussion about that, and I said that I was trying to figure out whether the commercial protocols of the MCML system could be made to interwork with the internet mail protocols. And of course, I also was honestly trying to break the barrier of the appropriate use policy, which said no commercial traffic was allowed. So they said yes. We set up and brought up the MCML system through a gateway, a translating gateway. And as soon as we did that and announced it, all the other commercial email guys said, wait a minute, we want to be in on this. So they got connected as well. And in that same year, 3 commercial internet services came along, UUNet, PSINet, and SurfNet out in California. So I think it would be incorrect to imagine that the intermediate level networks engaged with the commercial community. It was more like the commercial community came along and started offering and growing their own services. And they reached the point in 1995 where these commercial services were as big as or bigger than the NSF-net backbone, at which point NSF said we're shutting down the NSF-net. Those parties who were getting internet access from the intermediate level networks basically were told, we will maintain interconnection among the various intermediate level networks, but instead of using the NSF-net backbone, we're going to use what we call internet exchange points or network access points, again, underwritten by NSF for a finite period, after which they had to have a self-supporting business model. So NSF's decision actually created a market for commercial internet services, at least as I see it. And then legislation was passed a little bit later, around 92, if I remember right, that officially said that commercial traffic was permitted to be carried on the government-sponsored backbones so that the people using them could get access to all of the burgeoning products, services, and information in the commercial internet. So that's roughly, I think that if NSF and if the Federal Networking Council had not permitted the appropriate use policy to be changed, that we would have been a long ways away from having access to internet in a commercial setting. So the Federal Networking Council, of which NSF was a part, really deserves a lot of credit for making that policy decision.
And it sounds like the financial model was developed by these individual networks, had their own financial model for how the applications would be self-sustaining. It wasn't inherent in the internet itself. The actual financial models of those applications were on top of that as well.
Well, actually, let's talk about that for just a minute. When Bob and I were doing the original design, we consciously did not make any assumptions about the business models that might be used by the constituent networks, because we figured it could be anything. Government run, could be a private sector commercial thing, could be a not-for-profit, and we didn't care. Our assumption was, as long as the technology works, each of the component networks could pick whatever model worked for them, and they could change those models from time to time. UUNet, for example, started out as a nonprofit and became a for-profit, and eventually was sold to Metropolitan Fiber Systems for a couple $2 billion. So this freedom, this openness, this flexibility was deliberate. And I think the other thing I would say is that just speaking of networks alone, most of the networks didn't have applications. They were just there to provide connectivity. Over time, internet-based services started to arise, especially after the arrival of the World Wide Web, which comes in late 1991. Companies began to see how to use that layer, which is above the TCP/IP layer, to build applications. And of course, today we have millions of them, to say nothing of apps running on mobiles. So you can sort of see how the flexibility and freedom to add new parties, new players with new applications really essentially allowed the internet to grow in an uncontrolled, extreme way.
Mm-hmm. Certainly in a way that wasn't anticipated in the early days of TCP/IP, I'm sure. So.
If I could just make a really important point, we did not design the network to serve any particular application. It was simply to move packets of bits back and forth from point A to point B. And that was very deliberate. We didn't want either the underlying communications technology or the applications to dictate the design and implementation of the internet. We wanted it to be essentially isolated from that, so that we didn't have to redo the network every time a new application came along.
Yep. And early on, I don't think data security was a high priority in the development of the network, but as those applications have grown and the use of the internet has grown in very new ways, now data security is a real high priority. And we see the emerging blockchain networks, distributed ledger technology networks developing on top of the internet, hoping to address some of those security issues. Do you see any parallels in the development of these new networks on top of the internet? And is there anything we should take away from the early internet and make sure we incorporate those principles into the new solutions?
Well, let's before we get to the blockchain question, let me point out that security was not ignored. First of all, this system was intended to be a prototype for a command and control system for the Defense Department, and we'd be pretty silly not thinking about security. The problem we ran into, and I was working already in 1975 with NSA to look at how to build secured packet networks. The technology that we had available at the time did not include public key crypto, which is extremely important for key distribution. That we had more centralized key distribution capability, which we were experimenting with, not in the public internet, not in the one that the research community had access to, but the one that the Defense Department was working on. However, when public key cryptography popped up in 1976, the inklings of it came out from Whit Diffie and Marty Hellman at Stanford, but they didn't implement anything. They just said, here, if you had mathematical functions that had certain properties, then you could build this public key crypto thing. It took a while before that technology became available. And it wasn't available at the point around 1978 when I was trying to freeze the protocols and get things implemented and demonstrated. So this is not a mea culpa or an apologia. It's more a question of observing when certain technologies have come along. And I will point out that we have retrofitted a substantial amount of technology for security into the system since the beginning years. And blockchain is another example, of course, as you know, of an application of public key cryptography, digital signatures, and the like. So let's turn now to blockchain. I don't know if I'm well known, but I will say that when I'm asked, I frequently say blockchain is not the solution to everything. On the other hand, it has a very useful purpose when it's applied in the right way to the right scale problem. So I don't consider it, at least not yet, to be a place where you would turn to for extremely high bandwidth transactions. Imagine how many millions or more transactions must take place per unit of time at Amazon, for example. I wouldn't immediately think of blockchain as the first choice for handling that kind of capacity. On the other hand, for things that don't have huge dynamics, where you want to remember an event that has taken place or a transaction which has taken place over a period of time, blockchain has had a fairly good match to that requirement. I will say, however, that I worry about the cases where you have to remember for a very long time everything that's happened. For example, in the real estate business, it's important to remember transactions and transfers of ownership and other rights forever, because some of the deeds that are associated with ownership today have origins hundreds of years ago. I'm not 100% clear exactly how that works out for blockchain if you have to remember everything. On the other hand, if you don't have to remember everything forever, and it's a kind of a rolling effect, then blockchain probably works pretty well as long as the transaction rates are not overwhelming.
Also today, we have many blockchain networks that are developing in a manner very similar to the early days of the internet. We have networks that are forming, often using proprietary technology and creating solutions unique to their network. But at some point, these networks may want to connect together to share information. Is this a new opportunity for the internet community to find ways to connect these data networks together? Is this a new challenge for the Internet Engineering Task Force?
Well, that's a very interesting question, because I see blockchain as an application level kind of phenomenon, and the IETF tends to stay below the level of applications for the most part. But we can learn something from the internet's architecture and evolutionary experience, one of which is interoperability is super important. Having agreement about how things will interwork is very important. I have no idea, for example, whether independent blockchains can be made to interwork with each other. And I'm not even sure what that means. But if, for example, transactions that are remembered in one blockchain need to be recalled through another one, there'd have to be some way of making those references. Just like in the internet space, IP addresses and domain names are a very important lingua franca across the entire system. References to those things are understood by all kinds of applications. So I would say for the blockchain community, to the extent that they imagine that blockchain has some analogy, or that there is an analogy between blockchain and internet, multiple networks, multiple blockchains, you have to figure out what things should be held in common what things should be understood on an interoperable basis in order to allow new blockchains to be added to a growing system, if we're going to use the analogy of multiple networks and multiple blockchains. I think there's a lot of open space there, lots and lots of unanswered questions that would have to be addressed, not necessarily in the Internet Engineering Task Force, but possibly in other standards places that are focused on things like blockchain and blockchain applications.
Well, that's a very interesting point that you made, is that there are common communication protocols, standards for data that exist within the internet, that across blockchain networks, those standards don't exist. The data definitions in one blockchain network may not be applicable to another. And so there's a large amount of work that would have to be done to make sure we're speaking the same language. So that would be a large challenge. And I do understand the Internet Engineering Task Force, it's not really within their domain. So some new group would have to come together to help with that interconnectivity.
So, another thing that you could think about in terms of blockchain and its use is that, again, a kind of a layered view of things. There's the actual blockchain itself, the thing that's things are stored in the chain, the blocks are signed, and so on. And then there's the question of what's actually in the thing that's stored in the blockchain. So what is the vocabulary? What is the representation? What is the metadata associated with something that's of the transaction that's in the blockchain? You can imagine people working blockchains coming to an agreement with each other about the information and its structure and format that is captured in the blockchain, so as to make the transactions in the blockchain in some ways compatible. Mm-hmm. So that being able to fetch a transaction out of another blockchain, if there were a protocol for that, would mean that when you fetch the information, you understand what it means because you have common agreements about how that information is represented and formatted.
Mm-hmm. So to pull it all together then, the open standards were critical to TCP/IP and the early adoption and the early growth, and that open architecture, the standards group that made those protocols readily available at no cost, that was critical. Having a way to connect multiple networks together, some real practical experience seems to have been critical back then, is that that interconnection. There was a lot that was learned, probably a lot of changes that occurred in your thoughts about the protocols and how they would move forward. A creative platform for lots of ideas. Eventually the World Wide Web came in. That was a surprise to a lot of folks at the time, I'm sure. So all of these very open, it's a very open environment for collaboration, creativity, understanding how the applications would be applied. Those seem to be the key takeaways for new data networks, blockchain networks. It's that same openness, that same creative environment that will be critical to their success.
That's right. And let me just add one other observation. There was an organization created by a guy named Dan Lynch called Interop, which stood for interoperability. This was an exhibition that you could bring your hardware and your software, connect to a local gigantic Ethernet, and then demonstrate that you could interwork with everybody else in the exhibition. Of course, lots and lots of bugs were found as people prepared to get onto the network and to interact with each other. That served as a very powerful test of the utility of the products that were being shown, because you could show that they actually interwork with lots of other products, even though they were all independently put together. Of course, the reason they interworked is because they all followed the same standards. But the discovery of bugs and the fixing of bugs was intensified as people led up to the next exhibition of Interop. And that particular practice, I think, led to kind of a rapid closure of interoperability among very, very large ranges of products.
Mm-hmm. I attended many of the interops. They were fascinating, and I still have an image today of walking into a room where there were network monitoring protocols under development and new applications, and there were a series of computers, and everybody was there looking at their own network and talking about how they would manage the networks and the connections between them. It was real time right at the conference. It was a fascinating process to watch.
I wonder, did you manage to get to the one where somebody put a toaster on the internet?
I didn't see it.
We used to joke about this toaster net. We said someday your toasters will be on the internet. So somebody actually hooked up a toaster to the internet. You could send an SNMP packet or something to tell it how burned you wanted your toast.
Yep.
And of course, now looking back on that from the 2020 period, with the Internet of Things rapidly approaching and already penetrating into our environment, we look back at those sort of naive days and think, holy cow, we weren't all that off the mark. It's just that we thought it was kind of funny at the time. It's not so funny now. This is a big deal. It's important. Security is vital. Strong authentication of the devices is important. And our increased dependence on these autonomous chunks of software running these various devices is a big deal, because it's an artificial infrastructure that we are going to be increasingly relying on, which says it has to be more secure, more reliable, more resilient, and safer than it has been in the past.
Absolutely. And as we think about the Internet of Things, and those of us that have been looking at that for the insurance industry and the application of blockchain technology, you have to have an immutable record of an event that occurred on that device in order to pay a claim. So we've been thinking a lot about how blockchain technology might serve the insurance community and the Internet of Things community. But again, as you mentioned earlier, it's not a technology that we really want to apply lots of transactions, a high rate of transactions. So how might we still obtain that immutable record, but not take every transaction in from everything that's on the Internet?
Well, that raises two issues, at least. I mean, many others, I'm sure. First one is privacy, and the keeping track of transactions in which IoT devices are involved could easily raise privacy questions. What if it's a webcam, and what if it's one of the devices that has a voice interaction like Google Home? So there's a privacy question that would have to be dealt with if you're capturing transactions. The second way of dealing with scale, of course, would be to say, well, why don't I build the blockchain locally in the home, in a manufacturing plant, and capture the local stuff? Then the question will be, how do I tie these independent blockchains to each other in a way that's useful, but preserves all of the issues that I was alluding to? But by that means, you would at least not be forced to handle all transactions all the time from everything. You'd be building a kind of a hierarchy of transaction structures. But again, many standards would have to be agreed upon, and perhaps this topic has not yet been addressed.
Yeah, I don't think it has been addressed yet. A lot of people are thinking about it, but it comes back to many independent networks. In this case, it might be in your home, in a way of securely connecting them together. It always comes back to that very basic principle. We're going to have some open standards, open communication protocols to connect multiple networks together. So at the core of TCP/IP, it just always comes back to that for me. It's that open standard and that interconnectivity that makes it all work.
All true, and we're still using it. It's still, serving about half the world's population. So as the chief internet evangelist at Google, my job is to get the other half of the world up and running on the net. They tell me I can't retire until I get done with that.
Good. I hope that's true. Well, Vint, thank you so much for joining us today. I always appreciate your candor, your insights. It's great to talk with you.
Well, these are all topics of real interest to me, and I hope it'll turn out to be of interest to the viewers of this interaction.
Great. Thank you so much.